transformer is a piece of equipment that changes the characteristics of electrical energy from one electric circuit to another using electrical induction or magnetism. The change is usually a reduction or increase in voltage, also known as step up or step down. You see, it is easier to transport a higher voltage of electricity longer distances than it is lower voltages. However, once the electricity is close to the equipment that's going to use it, sometimes referred to as the utilization equipment, it's safer and more effective to be a lower voltage. A transformer does not create electrical power, nor does it have any moving parts. It changes electrical power from one AC circuit to another through induction. In order to understand the advantages and uses of a transformer, let's first look at the basic transformer parts. There are four basic parts in a transformer. The input, or primary connections, where wires or conductors are attached. The output, or secondary connections, again where wires or conductors are attached. Windings, these are also known as primary and secondary coils. And the last part, the core. The core is a large metal piece that helps make the magnetism work. Basically, two magnetic coils, the primary and secondary coils, are made up of metal that is highly conductive, such as copper or aluminum. They share the same field and transfer the electricity from one to the other. The transformer core is used to provide a controlled path for the magnetism generated in the transformer by the current flowing through the coils. The coils are wrapped around the core, and the specific properties of the coils are dependent upon the amount of times they are wrapped around the core. These wraps are often referred to as turns. The relationship between the wraps around the core from one coil to the other coil is called a ratio. In other words, if a transformer has a 4-to-1 ratio, and you introduce 400 volts on one side, the primary side, you would in turn get 100 volts output on the secondary side. Does that make sense? Let's take a look at a basic building transformer. Here we see the incoming power, also known as the primary power, coming in on the left side and energizing the primary coil. Then, through magnetism, actually induction, the electricity is transferred to the output or secondary coil. Again, there are no moving parts in the transformer, but the electricity is flowing through all these parts when it's energized. The size of a transformer and its components depend on the amount of electricity that is being used by the circuit attached to it. Transformer sizes are normally classified by a kVA rating. kVA means how many thousand volt amps the transformer is capable of providing. We'll talk about that in greater detail later. One of the most common types of transformers that you would find inside of a building is a dry type transformer. It's called this because there are no liquids used in the transformer to cool it. Therefore, it is dry. These transformers have enough space around the coil and core to allow heat to dissipate effectively and not cause the transformer to overheat when it is in use. Most dry-type transformers have outer metal enclosures so that the energized portions do not come in contact with people or other equipment. These transformers can be mounted on the floor or hung from the ceiling and even installed outdoors. They may have one set of coils because there is only one electrical circuit, also known as single phase, or there may be 3 sets of coils, which is common in a 3-phase distribution transformer. Usually, dry-type transformers are used for large electrical loads within a building's distribution system. Sometimes, smaller, specialty transformers are used to manipulate voltage for a small or single piece of utilization equipment to achieve a very specific voltage. These transformers are not intended for larger loads or systems. They're called buck-boost transformers or control transformers. Usually these transformer coils are completely enclosed, sometimes even surrounded by insulating solids or potted, meaning they are different from dry-type transformers in that way. Some places you might find a control transformer would be inside of an appliance like a dishwasher or a washing machine, a doorbell, or even used in a control circuit such as a motor control circuit. Buck-boost transformers are a little bit larger than control transformers, but they are both small. Many times they are used to transform the utilization voltage up by just a few percent so that the equipment can run effectively. Perhaps you have a building system voltage of 208 volts, and you have equipment that needs 240 volts to run effectively. This is a perfect example of where a boost transformer is used. Many buck boost transformers are auto transformers. An auto transformer is a transformer where there is an actual electrical connection between the primary and secondary coils. It looks something like this. You can see that there is a common connection to one side of the coil, and it is shared by the primary and secondary side of this transformer. Sometimes auto transformers have multiple points, known as taps, where the user can select a specific output voltage that they want to use. An isolation transformer is a transformer that has no physical electrical connection between the primary and secondary windings. In fact, most building distribution transformers are also isolation transformers. Usually, the change in voltage and current between primary and secondary windings occurs as a result of the shared magnetic field in the core. But in some cases, there's no need to change the voltage by the transformer, just a need to provide a good electrical separation in the circuit because a component in the circuit may be creating an electrical disturbance, also known as electric noise. An isolation transformer can help separate this noise from one part of the circuit to the other. Isolation transformers look just like dry-type transformers. The only difference is the coils, or windings, have a 1-to-1 ratio. Here's what this looks like. You can see the electric noise coming in on the primary side, and the output side has a perfect sine wave. The electrical noise was lost. Depending on the size of the load and the amount of expected electrical disturbance in a circuit, transformers can be sized appropriately to handle and mitigate these disturbances. The rating of these transformers is called a K rating factor. Transformers that can handle large amounts of electricity for distribution from multiple buildings and factories often become warm because of the large amount of electricity they are using and need to be cooled using liquid such as oil. These are called oil-filled transformers. In an oil-filled transformer, the windings and core are submerged completely in the cooling oil. The housing or casing of the transformer usually has cooling fins or some other mechanism for the warm oil to come in contact with a large surface area that can be cooled externally, similar to a radiator. These transformers are usually located outdoors for safety reasons. You may see them in a neighborhood or outside of a business. They're sometimes referred to as substation transformers. Here we see some examples of oil-filled transformers. Let's try our hand at some of the math that is used when calculating the size of a transformer, or the amount of work a transformer can do. First of all, you should understand that transformers are normally sized in kVA, or kilovolt amps. It's a unit of measurement that reflects the amount of work a particular piece of apparatus can accomplish. K, in this instance, stands for the number 1000. V stands for system or circuit voltage. A stands for system or circuit amperage. To determine kVA, you must have at least two other pieces of information: the operating system voltage of the transformer, V, and the maximum load amperage, A. To calculate the kVA rating of a single-phase transformer, use the formula kVA equals voltage times amperage divided by 1000. To calculate the kVA rating of a three-phase transformer, use the formula kVA equals volts times amps times 1.73 divided by 1000. Remember, transformers are made in standard kVA sizes. So once you determine the kVA size that's needed, you have to round up to the next available nominal size. Let's look at an example. For instance, a single-phase transformer with a voltage of 120 and an amperage of 200 would calculate at 120 times 200 divided by 1000 would equal 24 kVA. We would have to round up to the next standard size kVA, which would be 25. Let's look at a three-phase example. 208 volt transformer that uses 360 amps would calculate at 208 times 360 times 1.73, because it's a three-phase transformer, divided by 1000 would equal 129.54 kVA. We would round up to the next standard size transformer, which is 150 kVA. You can also use these formulas in reverse to find other values. If you already have the kVA rating and voltage, you could figure out the maximum amperage like this. 100 kVA single-phase transformer. Well, we know that 100 kVA is equal to 100,000 VA because K stands for 1,000. VA is the voltamps, so then we divide. 100,000 divided by 120 equals 833.33 amps. How about a three-phase transformer? 25 kVA times 1,000 would make 25,000 VA. It's then divided by 1.73, which equals 14,450. You then divide it by the voltage, 208, which would give you 69.47 amps. When making transformer connections with conductors, it's important to understand that the connection should be solid and tight. Although transformers do not have any parts that intentionally move, the magnetism that occurs in a transformer may cause a slight amount of vibration, which could loosen the connections. Loose connections can and usually will create overheating, which could result in damage to the transformer. Be sure conductors are clean and free from corrosion and dirt. Be sure to follow manufacturer's recommendations and instructions when making transformer connections for items such as tightness and torque, type of connection or connector, the temperature rating of connectors, and insulation of connections. Transformers should be de-energized when you are working on them if at all possible.